Hello everyone. In today's teaching lesson, I want to show you how to do credit analysis for for people applying for loans. This could be through a credit union, could actually be through a credit card company, it could be a bank, it could be a home loan, a personal loan, business loan, school loan, something like this, and how to look at different features in the data set to try to determine historically, we know who has repaid a loan, who hasn't, and if your profile matches somebody who hasn't repaid a loan because your features match up with other features of people are failed to repay for whatever reason, then the loan will not be issued. But if your features are substantially similar to other features of people that have historically borrowed money and have a successful history of paying back the loan and paying the interest and the principal back, or paying back the interest of the loan, and paying off the money too. Sorry, lost my train of thought for a second. Then we will issue a loan to this type of person. Okay, so normally I show you the data set at the end, but I'll just take you down here quick. So I did list the data set, so you can go ahead and grab that. Let me take a quick look and just see what this thing looks like. So I'll put this in the notes. I'm going to share all the notes with everybody. I always share all the notes when I post the video. Let's just take a quick look at this thing. Oh yeah, there it is. So you see some details. It's kind of a data dictionary, sort of. And then here's the download CSV file. So that's where I got the file. I actually put it on my desktop, and it's right here. So you have how many features? I think it's 55. Yeah, 55 features. And then you have things like employee title, employee length. Wait, is employee an actual employee? Because this would be more like customer. Let's see what it says. Oh, just job title. Not sure what the emp means. Okay, so they have some weird naming convention. But you have the job title, the length of work that the person has been at, the state that they live in. Do you own, do you rent, annual income, verified and not verified. That's actually very important. Debt to income, that's important. Annual joint income, right, for spouses, verification of joint income. So here's all your features. It's pretty rich, 55 features. I found this data set online. I found a couple that I was looking at before I started recording the video, and all these data sets are different for any kind of loan. They're going to capture different features and report on those. But any kind of feature that you have, it's going to be important to train and test a model and be able to make predictions into the future about whether you should issue the loan to this customer or this potential customer or not issue the loan. Okay, so that's what we're looking at here today. Let me go ahead and refresh this. The data sitting in a CSV file on my desktop. Okay, so I'm going to load the data and then just do a quick sanity check. Are there nans in here? What are the data types? D type is data type. I want to see the columns and then the overall shape and then the data frame head. By default, it gives you 5. If you put numbers in here, like 10 or whatever, I'll show you the first 10. If you leave it blank, it's 5. So we have title, length. We already determined this is kind of useless. I don't know what that means. Home ownership, and so on and so forth. The first thing we're looking at is null. So we're summing up all the nulls. So out of how many records? I think this is 10,000 records. Yeah, so we have rows, comma, columns. So this 10,000 rows, 55 columns. So about 8% are null here. Employee title and length of service. That's how long they've been at their job. Home ownership. So these are all filled in. Anything that's filled in is great. Anything that's mostly blank, like this is 85% missing. Annual income, that is kind of a concern. I don't think we can use some of these features. Debt to income joint, but that would be very useful to have. We don't have it. If you don't have the data, you don't have it. That's unfortunate. I've worked in many places before that want to do these amazing things, but they don't have the data to do it, so you simply can't do it. But if you could go back and capture that data, backfill it, forward fill it, go to another data source and fill in the data. You could impute missing values. Like if you have 8% missing here, you could impute the 92%. You could impute this 8% from the 92%. You can't really impute 15% from 85% missing. That's not going to happen. If it's over half, you're really not going to impute anything, right? So we'll focus a lot on these not missing values because those are the most helpful. Here we're missing 12%. Not the end of the world, but I'd like to see more complete. This thing is kind of useless because it's just too many records missing. Now we're looking at the objects and the float and the int, and int is 1, 2, 3, 8, 9, 10, things like that. Float has a decimal, so anything with dollars and cents can be a float, and an object is everything else. Okay, so That could actually be a date. It could be a name, a string, a bunch of different things. And then we're just looking at the column names over here. I just wanted to print that just so I have a quick understanding of what the data consists of and what kinds of things we're going to be dealing with here. So here's the view of the data frame, the first 5 rows. So we see some nans already. These are missing. Nothing we can do about it. Some historical. Num historical failed to pay. Okay, so if you're failing to pay, I want to know about that because that's going to impact my ability to give you a loan. If you fail to pay on another loan that you took out a few years ago, I'm probably not going to issue you a loan today because it's just bad business. Like you've already proven you can't pay off the loan, right? We're not going to go down that path again. We already know this is a bad credit type of person. So we're just looking at the data and visualizing it very quickly. I mean, just with our eyes, we didn't even create any charts. I only create one chart, I think, at the end. It's not like a big planning and charting type of exercise, but it is big on machine learning. So I'm going to go ahead and do some encoding for all of these categories that are objects. So employee title and length of service, if you go down here, I know these are on the right. So global configuration engineer, length of service, that should probably be a number actually, but it's coming in as a non-numeric number. It's coming in as an object. That's okay, we can handle that. And these are the states that people live in. Here's mortgage or rent. So this guy has a mortgage, so I probably would rent, or probably issue a loan to him because he already has one loan. These guys are renters. Maybe they don't even understand what borrowing money means, right? Because they're renters. The home mortgage guy, he definitely understands. So that's one thing we'll look at, annual income and so on and so forth. But I want to go ahead and convert everything that's non-numeric to numeric. That's why I have my label encoder over here. So machines, computers, and systems understand numerics very well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Computer knows exactly what that is. The computer has no idea what security supervisor is. It has no idea customer service, assembly. I don't even know what that means. Warehouse office clerk. I know that one. But the computer doesn't know that. And global configuration engineer, computer has no understanding, comprehension, or wherewithal of this thing whatsoever, right? But we can encode that as a 1, 2, 3, 4, 5, 6 number, as long as this is numeric and it corresponds to any global configuring engineering person, we can work with the 1, 2, 3, 4, 5, 6. We can't work with this, right? But once we label and code it, then we can work with it. So we have to encode this or somehow vectorize it. Vectorize is kind of a different concept. Encoding is fine in this example. So we're going to encode that. I'll click the cell to refresh it, control enter, it runs. Okay. And then the reason we're doing this encoding is because if you look over here very close, where is the loan status? Okay. So loan status is actually a string, current. So these loans are all currently being serviced and they're in good standing. Nothing has been defaulted or anything. But I want to go ahead and convert that current to some type of numeric. That's what the encoder is doing. So charge off is 0. So that's a bad loan that's been written off. We're not going to be able to collect on that guy. So I'm not going to loan him any more money. Okay. So I'm going to look at the other features that are relative to this charge off feature and determine if any of these features substantially match other features for new loan applicants. I'm going to say no to them because we already know that this guy is a deadbeat. He's not going to be able to repay his loan, right? So currently being serviced is fine, fully paid is fine, the loan has been paid off, and grace period. I think that means, this is brand new data to me, I think that means they haven't paid a loan within 30 days, but it's still within the duration of good graces with the loan provider. I believe that's what that is. This is late, 16 to 30 days. Oh, so I think this is 15 days. So they haven't paid on the pay date, but they're less than 15 days late. This is 16 to 30 days late, and this is 31 to 120 days late. So anything in this bucket or this bucket, I don't like that. I don't like this because we've lost all the money on this guy. He's a deadbeat. He got away. But 1 is totally fine. That's what we'd expect. This is fine. The loan's paid off, so everything there's nothing really to do here. That one's done. And grace period is okay. We're within 15 days of when it should be paid. Not the end of the world. Hopefully the guy's going to call in and say, hey, I'm about to make a payment. Or we can call collections and they can call that person and request a payment. But still, it's not too bad if you're in the grace period. Okay. So here's the first methodology that we're going to look at, log regression. So it says regression, it's actually a classifier. We're looking to make certain classifications based on these labels. These are the 5 labels: charge off, current, fully paid, grace period, late, or very late. This is a little bit tardy. All right, and this is very tardy right over here. Okay, after that, it's probably going into charge off or some kind of collection or something like that. Once you get into 120 days, that's not good. So, so the first model here is log regression. It's actually a classifier, and we're trying to set the target variable right here as the we're making predictions about whether or not the loan is going to fall into one of these 5 categories: charge off, current, fully paid, grace period, late, or very late, right? That's what the y is for. The x variable is the independent variable, so that's all of the rest of the features in the pipeline, the data pipeline that we're looking at, right? And the accuracy of this is 0.954, and the area under the curve is 0.813. So closer to 1.0 is better. 0.954 is actually very accurate. So 95.4% of the time, the model is able to make predictions, and based on the test set and the holdout set, these predictions are actually correct, right? So we have the holdout set and the test set and the training set. We're saying we're not going to expose the model to every single record in here because the model will basically memorize everything and it might not actually learn anything. We want it to learn on a certain amount of data. It's going to be about probably 80 to 70% of the data, but the holdout set, the data has not been presented to the model yet. We want the model to look at its prediction and compare it to the actual holdout set, which is not seen, and say how accurate is that. 95.4% of the time, it's actually accurate, okay? So now we have a confusion matrix. We know that 1, the loan is currently being serviced, okay? So most of these fall into this bucket. If I can hit Control-Enter, we'll refresh it. Most loans are currently being serviced, so that's why you have 1843 over here. This is the predicted label, and this is the true label, so most of the time it's correct. You can see there's a couple little mistakes over here. The predicted label is 12 over here. I'm sorry, is 1. The true label is 3, so it's saying this should be currently being serviced, but it's actually late. All right, so the computer model here is making a prediction. It's making a couple mistakes, but it's only a handful, 95.4% of the time. If it says issued a loan, we're going to issue a loan, and the borrower is going to pay back. Maybe 5% of the time, the borrower won't pay back. There's some extenuating circumstances. There's some weird scenario that came up. The person went bankrupt all of a sudden. Maybe they had some kind of financial hardship at work. Maybe a health condition prevented them from going to work, and they can't make payments on loans. It could be a bunch of different things, right? But 95% of the time, we are going to make loans to people that are going to pay them back. 5% of the time, we might lose money, and there's really nothing you can do about that. You can't get this up to 100% necessarily, unless you tighten up the loan conditions or the criteria. But then you're going to miss a lot of potential opportunities to make money because you're going to pass on people that legitimately will repay on the loan, but you're going to miss this person and you won't be able to earn interest payments from this individual because you passed on the loan, right? So you can tighten up your lending conditions, but you're going to leave a lot of money on the table because you're only going to issue a small fraction of loans because your lending constraints are so restrictive now. You're not issuing most of the loans, right? You're keeping the money close to the vest. So here we're looking at a feature importance exercise. Okay, Control-Enter to refresh it, and we're going to plot the statistical significance of each of these independent variables on the predictive variable, right? So the predictive variable is loan status encoded. Okay, we're dropping loan status encoded and loan status because these are extremely highly correlated. You're going to have multicollinearity here between these two. And if I didn't drop the second one with this first one, everything would go into this bucket, right? So we want to drop these two and just look at which features have a statistical significant influence on the dependent variable. That's this right here, right? And all the other features are the independent variable. So we're doing the XGBoost regressor. There's a few different ways to do this. So I think this looks okay. It's a little bit messy. A lot of things are kind of like pushed together. It's a little bit hard to read, and it's not in any order. So let me go ahead and refresh this in descending order from highest to lowest. Okay, all we're doing is sorting right now. We're sorting the index. So again, we see how everything shakes out, and this is helpful. But again, everything is smooshed together here, so I can't really tell what this is. So I'm going to look at just the top, I'm going to say 30 features. We have 55. Some of these are contributing almost no benefit to the target variable. Right here, you can see at the end here, you probably have 10 that are de minimis. It's not even registering even 1%. So I'm going to kick those out and say, just show me the top 30%. And I think something happened here. Okay, I forgot to import a library. So let's redo this. Okay, it's working. Excellent. So we have the top 30 features: balance, paid total, paid interest, paid tuition, paid late fees, loan amount, down to loan purpose, right? So loan purpose has about 1% statistical influence on the ability of the loan to be repaid. That's interesting. I thought it'd be higher, but you know what? It is what it is. The balance of the loan has most of the influence on the target variable, right? So I think that totally makes sense. Paid total and the paid interest. So these first three totally make sense. The last one, I thought the loan purpose would be a little bit higher. Like if you're borrowing for, I don't know, a home or a school loan or a small business, I think that would make a difference. But according to this, it's the 30th most influential feature. So it's doesn't have a lot of weight on the target variable, but that's okay. It is what it is, right? So we have the top 30 features here. Now we can do something pretty cool. We can go ahead and pre-process the pipeline again, include only these features, because these are the top 30. If we look at all these other features over here, we have about 25 or so that really have no influence on the target variable. So why would we even consider using those? It's probably going to mess up the model. It's going to mislearn something or learn something the wrong way, or take a long time to run and not converge quickly. We want the models to be highly performant and to well, not only run quickly, but produce accurate results too, right? We want that 95% or better type of accuracy. So I'm going to go ahead and rerun the model, reprocess the pipeline. Here's all the numeric features that we saw before, right? Those are the top 30. And we are going to pre-process these, impute them, and scale them so everything is in the same relative scale. Okay, and then I'm going to make a prediction about a new customer. So given those top 30 features, I'm going to say account, sorry, it's hard to read this. Account never delinquent. Oh, account never delinquent. Okay. And the value is 92.9%. So where does that come from? If you go back to the original data set and search in the headers here, let's see where that says. Okay. So let's call them AJ and never delinquent percent. Okay. So they're saying it's 100% never delinquent. If it's slightly more delinquent, that's better. I'm sorry, that's worse. So close to 100 is better. Further from 100 is worse, and this goes down to, wow, some pretty low numbers down here, 100% down to 14%. So this guy I'm certainly not going to lend to, 14% likelihood to pay off or never be delinquent, right? Like we want that close to 100%. So that guy is probably going to get, probably not going to get approved for the loan. But that's what we're looking at. These features, we're going to fill in these numbers because here's a new customer coming in. These are the features when we collect the information from the customer. We're going to have them fill out the loan application, right? All these features are coming straight from the application. We dump it into this model, balance, debt to income. That's pretty low. Debt to income joint, low. We want these numbers low, right? We want this number high. Once we have this set up, what is this? Total debt limit. Okay, so he has a limit. If you had unlimited debt, that would be a little scary. I don't know if I'd lend to that guy. Once you have all these numbers set up, you can go ahead and rerun this. I forgot if I ran it. I think I did run this. I'll rerun it again. Okay, and we have the predicted status 1. So this is a perfectly fine loan. It's being serviced. It's current on the books right now. According to all these criteria, we just trained the model and made a prediction about whether or not we should issue a loan to this guy. If this person meets the criteria, right? This man, woman, or joint borrower, whatever it is, meets this criteria, we're going to give him a loan because that is a very safe type of borrower, right? So I'm very happy to lend him the money. He's going to pay us the interest, and we're going to have a good relationship with this guy. So here's a different model. This is a random forest classifier. Again, we used the log regressor, which is actually a classifier. I don't know who came up with that name. I think it's hilarious because it sounds like a regressor. It totally is not. So here's a random forest classifier. This is truly a classifier. We have almost the same code that we saw before, but different model over here that's going to produce a slightly different result. Last time we saw 95% accurate. This is 98% accurate. So this is even better than before. I'm thrilled with this accuracy. 2% of the time we're going to make loans to people that are going to default, but it's better than the model that we saw above that was 95% accurate. That back then that was impressive. This is even more impressive. I'm going to make another prediction with this new model now, right? We are using the prediction of this random forest classifier right here. I'll highlight it just to show you. Okay. And what is the output down here? It's still running. Okay. 98% accurate. Area on the curve 79%. That's fine. Let's go with it. Predicted loan status 1. So predicted the same as the other, but it's more accurate. It's 98%, not 95%. So this looks good, right? Accuracy measures the proportion of correct instances, both true positive and true negative, out of all of the instances. That's what we're getting. That's where we're getting. It's 98%. So how many instances are true, right? We don't want to see falses. We want to see a true positive or a true negative. True positive is we approve the loan and they pay off. True negative, we disapprove the loan and we know that the person wouldn't have paid off, okay? We don't want a false positive or a false negative. Area under the curve quantifies the ability of the model to distinguish between different classes, right? And this characteristic curve, receiver operating characteristic curve, abbreviated ROC, plots the true positive sensitivity against the false positive, okay? So we want true positives and true negatives. We don't want false positives, right? And we're going to try one more instance here with a gradient boosting classifier. That was a random forest classifier. This is a gradient booster, just to see if we can boost the result a little bit and get just a slightly better performance. We got 98% last time. That's why it's good to run different models, right, and see how they perform over your data, because you never know. A different data set will generate different results from different models all the time, right? You have to run different models on the data to understand all the nuances of the data, any noise in the data, right? And make sure that the model can learn, and more importantly, make predictions on data points that it hasn't seen yet, right? Because you can have new customers coming to your business asking for money, and you've never seen this guy before, but he will have a profile, or she will have a profile similar to other customers that you've interacted with before. And then you can fit them into that bucket. Is this a good loan? Is this a good prospect? Is this a good risk, right? Or the opposite, is it a bad risk and we want to avoid this, right? We're not going to approve the loan. So that's why we're doing this, this classification, training, testing, and making predictions into the future once the model has been learned. That's what the whole point is, okay? So the model is chugging along here. This one is a booster, right? It says in the name, it's a boosting classifier. So it runs one model and then another and another and another in an ensemble fashion. The random forest classifier performs very similar but slightly different because it performs everything in parallel. So it tends to run a little bit faster on the data set. This is sequential, right? So this is serial running through different models, different ensemble models, one after another after another. And the random forest classifier is running through all the models in parallel, right? So that's the difference between these two models. And I've talked about that in some of my other videos too when I get more into the classical machine learning techniques. Okay, so I had a quick sip of water there, and now we're getting 0.97%. Okay, still decent. The last model was a little bit better, 98% accurate. This is 1% less accurate. I will rerun the predictor over here. We trained and tested the model. Now we're going to make a prediction. Okay, and let's see what comes back here. The predicted value. Last time we got 1, right? Predicted status 1, which is totally fine. This is a good loan for a good customer. They're paying on time. They're paying all the interest, and the business is happy because you're making profits for your bank or your lending institution, your credit union, your credit card, whatever outfit you're in. You're collecting your interest payments, so you're making a profit for your enterprise. So that's good. Let's see what label this comes up as. I'm guessing a 1 because the accuracy is 0.97. Pretty close to what we saw before. In between the log regressor and the random forest classifier. This is XG boost classifier. Let's see what comes back now. I'm guessing 1. And again, it's looking at all of these values, right, for all of these features. Annual income, balance, debt to income. We want this to be low. We want this to be high, right? The percentage of paying off the loan amount, the lower, probably the better. If they borrow $1 billion, is that guy going to pay off $1 billion? Maybe, maybe not. If he borrows, this looks like 280. Is that small? Oh, only 28,000. Okay, probably this guy or this girl is going to pay off 28,000. That's not a ton of money, right? The more you lend, the more risk you expose yourself to the person not paying back, right? So usually the loan amount lower is better, although you're not going to make a ton of interest on this, right? If you had a whale as a client and you're lending them $10 million, you're going to make a lot more money on that person over the duration of the loan. But then also, you know, if the guy decides at the beginning or halfway through the loan period not to pay back, then you're going to lose a ton too, right? So those are bigger risks to consider. Number of accounts, and yeah, also how many open credit lines does the person have? 10 sounds like a lot, okay? But if the person has been servicing all these loans, this could be actually like credit cards. You could easily have 10 credit cards in your wallet and have no balance on any of them, or maybe you use one, the 9 just lay dormant, and you pay off the balance at the end of the month. So that's totally fine. That's something else we would need to know about, right? So the model ran 97%. We got 1. That's just what I would expect because the other 2 models produce the same. So all 3 models are producing decent results here. All of these people that have this criteria or this profile, this risk profile, it would absolutely lend to this person. This is no brainer. It's a good risk. They're going to repay the loan. And of course, the numbers are going to come in slightly different, right? Maybe this is 6.9 or whatever. You would get that from the loan application. You just plug in the numbers here, and then you'll see who you should be issuing your loans to and who not to issue those to. Okay, so here's just a quick and dirty plot to show you the overall performance. Random forest is pretty close to perfect. I think that was 98, and the gradient boosting was 97%. So both models are performing well. We could go with either one. Maybe the random forest is slightly better. But they're pretty close, right? They're both doing the job. They're just doing exactly what it's supposed to do. So here's the data source, and we're at the end of the lecture. Hopefully that was interesting and fulfilling. Hopefully that was satisfying, and you learned a couple new things. I actually learned a few new things putting this teaching lesson together, and my hope is that you learned something new too. It's great to learn something new every day, right? Okay, so that's very much it. I'm going to wrap it up. Thank you so much for your time today, and enjoy the rest of your day, everybody. Goodbye.